So we're ready to go. Go over here. And an electronic is thrown into this one too because it's just one slide. It's real easy. So we're dealing with thermal excitation. So that's what we're focused on with these partition functions. And so we need to understand in each of these cases, whether it be translation, rotation, or vibration, what is the energy equation? Because we have to use those energy levels in the Boltzmann distribution. So here we are now in vibrational motion where we're using a harmonic oscillator, and the harmonic oscillator has an equal ladder of states, meaning all the energy levels are equally spaced. If you look at the potential energy diagram, it kind of looks like a particle in a box. It's a one-dimensional system, but notice it's a parabolic box. It's a parabola. You know, for the particle in a box, it was a square box or rectangular. It went up to infinity, right? And so then the energy levels were not equally spaced. They went up by by n squared, right? So these energy levels in a particle in a box were not equally spaced. But notice how this box gets wider as it goes up. And the harmonic oscillator, that parabola, is just perfect to bring these energy levels down. You know, as you widen the box, the energy levels drop. And so in a harmonic oscillator, the energy levels, the potential energy surface widens just enough so that the energy levels are equally spaced. It's just a nice feature of the harmonic oscillator. So this is the default assumption for vibrational motion. And we talked about internal rotation with the dichloroethane molecule and how the harmonic oscillator approximation fails for that vibration. It also it fails for anharmonicity's sake when you have a bond that's of a heavy atom that's being stretched, like the iodine molecule. So there's other places where this harmonic oscillator assumption fails, but for most of the situations, it holds pretty well. So then we can put these energy levels into the Boltzmann distribution. Okay. Now, where do we want to put 0? Most of the time for our analysis, we put 0 down at the V equals 0 level because we can't actually get below that. But for some calculations, it's useful to put it at the bottom of this potential. We'll talk about that in a second. So we start out with V equals 0 being 0 energy, and then V equals 1 is epsilon 1, and then V equals 2 is 2 times that energy, 3 times, 4 times, it goes on up. So we have a couple of choices. We can locate the energy at V equals 0, or we could locate it at the bottom of that potential energy surface. And we'll see those in the Gaussian output. You'll see BOT or 0, or V equals 0 in the output. So those are our two choices for where we locate 0 energy. Now this is the partition function. The definition of the partition function is that sum of all of those Boltzmann factors. Again, these are singly degenerate, so even though G should be in here, G is equal to 1. So this G of V, but all G of V are equal to 1. So it gets omitted sometimes, but y'all pointed that out last time or a few times ago. Very careful eye that you have, and so I'm glad that you did that, so I can emphasize that every time it disappears. And so here's what we have for that partition function. That if V equals 0, then we have this e to the minus 0. If for the next level it's e to the minus 1. The next level it's e to the minus 2 times e to the 1, e to the E1, because it's an equal ladder of states, and so we just jump up to 2 times E1, 3 times E1, 4 times E1, and so on. So that's just a nice, now it's an infinite sum, so where do we stop that infinite sum? Well, we're in luck, okay? Some infinite series converge, okay? And this is one of them. So if we look at this infinite sum, it looks a lot like this if we define our variables correctly. So it starts out, e to the minus 0 is 1, so that's pretty easy. If we treat this like x, then look at this. This piece right here is x squared. You see that? And this piece here is x cubed. So everything that I've circled is x. And so when you have 1 plus x squared plus x cubed, etc., this converges to this variable, to this function 1 over 1 minus x. And so that is our partition function, 1 over 1 minus x, where that epsilon 1 or E1 is equal to HC nu, right? And the nice thing about this is an exact solution. It's not an approximation. You know, for the translational motion, we said that the difference in the quantum states was infinitesimal, so we could integrate over n. And that was an approximation. We said, well, you know, it may not be infinitesimal in these differences, but let's assume it is. For room temperature, we have a lot of energy levels populated, so we'll assume that delta n is small, and we'll integrate. We did the same thing with rotational motion. You know, even a small molecule like carbon monoxide, we determined had 25 or 30 energy levels populated at room temperature. That's what we looked at last semester. And although that's not an infinite number of n's, still the assumption is that the difference between the rotational j values are insignificant, so we could integrate over j. So those were approximations, but this one's not an approximation. This is actually a sum that converges. So this is an exact solution for the partition function. Now, I'm pretty sure you don't remember this, but like the first or second lecture in pChem 1, we talked about Boltzmann's distribution and Boltzmann's work, and Planck using Boltzmann's work to solve the blackbody radiator. He said if we just treat the blackbody radiator as a bunch of little oscillators all having the same frequency, then we can get the population of those oscillators. This is the equation he used. So this was the result from Boltzmann that Planck used to solve the blackbody radiator, and it was the vibrational analysis and this infinite sum. So he could come to this conclusion that if we have an infinite number of oscillators inside this hot object, this is the spectrum we should expect, and he solved that problem, the blackbody radiator. Okay, so this vibrational partition function is shown below, and this is sort of a plot of those things at different temperatures. So at low temperature, we have, again, most of the molecules in the ground state. This is like a little bar chart. The little blue probabilities are shown. And so it's mostly probable to be in the ground state, but there's a little bit in the first excited state. And then at a little higher temperature, you see there's more excitation and less in the ground state. And at a higher temperature, still there's more. Now, where is the thermal bath in here? This is beta times epsilon, but that may not mean much to you. Essentially, that is the spacing divided by the temperature. And so this is saying that the vibrational temperature divided by the room temperature is equal to 3. And so this little gold bar relative to this energy level, so this was 0. New. I think just keep it with the, yeah, let's go that. New. And then this is 2 times that, and 3 times that vibrational frequency, and 4 times that vibrational frequency. You know, here we're coming in at 1/3 of that, the difference in those energy levels. Here, when theta V over T equals 1, then this is the thermal bath. It's equal to that first excited state. So we still have a lot of molecules in the ground state. We have more in the excited state, but we have even some molecules in the second and third excited states. Okay, now it's a little bit higher than that first excited level, and we get even more excited population. And then here at this last one, this is what we have when the thermal bath is equal to around 4 of those levels. We have excitation all the way up here. So we get much more excitation in vibrational motion as a function of temperature. Okay. Let's look at how this partition function behaves with temperature. So here on the x-axis, we're looking at temperature in terms of multiples of the vibrational temperature. So, you know, way down here, this is equal to 1. And so when we get below 1, there's this curve to the partition function. When we get much above 1, it's definitely above 10, it's just a linear function. So let's look at how this equation, it's a pretty complicated equation, and this is a skill that I'd like for you to have. Like, this might be a written problem on the exam, okay? And that is, here's this crazy equation. How does Q, what happens to Q if temperature goes to 0? You can see it from the chart, but let's use the equation, okay? So as temperature goes to 0, it's hard to know what Q is going to do, looking at the equation. Would you agree with that? I mean, look at that equation. And I say temperature goes to 0, what happens? Okay, so what we do is we walk through. So we go sit on temperature and we work our way out of this mess. So deal with that first fraction. What happens when temperature goes to 0? That fraction blows up to infinity. You see that? It's in the denominator of that fraction. So just take little baby steps. I could do that first baby step, and I could see that that fraction is going to go to infinity. Okay. Now, if that fraction goes to infinity, what happens to e to the minus infinity? And here you might have to think of the e to the x function. So e to the minus x. When x equals 0, it's 1. And then as x gets bigger, it's e to the minus, bigger number, and it gets down to 0. So it's going to go to 0 as that piece in the exponent goes to infinity. Okay. And so if that goes to 0, what is the denominator? It's 1 minus 0. And so 1 minus 0 in the denominator is going to end up giving us 1 over 1, which means Q is equal to 1. So that's not too bad, is it? So you give a really crazy equation, and I ask you, how is this equation going to behave with temperature? Work your way out of it, one piece at a time. And I would love, you get full credit if you show those 4 steps, right? If you just say Q goes to 1, you haven't shown me that you can explain it. I want you to explain it to me. If this was a written problem, I want you to break it into pieces like this and say, well, temperature goes to 0, then this fraction goes to infinity. This fraction goes to infinity, then e to the minus of that fraction goes to 0. And if that goes to 0, then we have 1 over 1, which is 1. Okay, let's do this one now. Let's go to, what if temperature goes to infinity? So now how does it behave as temperature increases? Okay, well then that fraction is going to go to 0, right? Because you got an infinity in the denominator. And if that fraction goes to 0, then e to the minus 0 goes to 1. And if that goes to 1, then we've got 1 minus 1 in the denominator, which is going to give 0, which means that Q goes to infinity. So as temperature goes to infinity, Q goes to infinity. As temperature goes to 0, Q goes to 1. And that's the behavior we would expect the partition function to do. Remember, it is a measure of the number of energy levels populated. So as temperature goes to 0, we're going to have 1 energy level populated, and that would be the ground state. So in those other approximations, like the translational motion or the rotational motion, the temperature dependence of those approximations would go to, Q would go to 0 as temperature went to 0. But that shows you that they're approximations, because it actually goes to 1. It doesn't go to 0. When you drop the temperature to 0, Q goes to 1. Okay. So now let's think about the total vibrational partition function. We can assume at high temperatures that this just becomes a linear function of temperature divided by the vibrational temperature. But let me emphasize this right here. So this is for one particular vibration that we've shown. This is an equation for one particular vibration. Every vibration has a partition function. So this is for all vibrations. It's the product. That's the other thing. With energies, when we're getting the total energy of a system, we add the energies. It's the sum of the energies. But when we want to get the partition function is the product of all of those partition functions. So for the total molecule, we would have the translational partition function times the rotational partition function times the vibrational partition functions. All of those multiplied by each other would give us the total. Okay, so this is just showing you that. And so this is a nice, again, we can use that vibrational temperature. So this is a very simple equation. Once you convert them all to vibrational temperatures, then you just have each individual vibrational temperature compared to the temperature of the room. And then you have the exponent, -1, etc. And then you just multiply all of those to get the total. Now with 0-point energy, if you use the bottom of that harmonic potential, then this equation becomes this right here. So we're not going to use the bot equals 0 ever in this class, but I always put it in there because Gaussian shows it, and I don't want you to look at the Gaussian output and be confused. So that's why I keep including it. Okay. So the main take-homes on this slide is that all the vibrations in the molecule would have their own partition function, and the total is the product of all of those. Okay. Let's look at some actual Gaussian output for our molecule, the hypochlorous acid. And so we have the rotational temperatures shown here and the vibrational temperatures. There's 3 of them shown right here. Okay. And so let's review. How many degrees of freedom does this molecule possess total? Okay, from the fall. So what is the equation for total degrees of freedom? 3n. That's the vibrations. So you got the first part of that is 3n. That's the total. So 3n. And remember, every atom can move in 3 directions. So that's where we get the 3n. So just because we put atoms together in a molecule doesn't mean we lose any degrees of freedom. Every atom has 3n degrees of every atom has 3 degrees of freedom. If there's n atoms, we have 3n total degrees of freedom. Okay. Now, if we want the molecule to stay together, some of those translational freedoms for each of the atoms turn into vibrations and rotations, right? So that's where we get the translation rotations. So there's 3n total degrees of freedom of motion, always. 3 of those are translations. So the whole molecule can move x and y and z. And we took that into account when we had that translational or thermal wavelength. There was one for x, one for y, one for z, and that's where it became cubed. Okay. Then we have 3 rotational degrees of freedom. We have 3 rotational constants for an asymmetric molecule. If it's a linear molecule, how many do we have? Yes, we only have 2 rotations for a linear molecule. And so then 3n minus all of these things that are not vibrations gives us the vibrations. So we figure out the vibrations by process of elimination. We have 3n total degrees of freedom. We eliminate the translations, we eliminate the rotations, and that's where the -6 comes from. So the 3n minus 6 means we're eliminating the translations and rotations, and everything else is a vibration. So we have 3n minus 6 vibrational degrees of freedom. Of course, in this case, we have 3 atoms, so 3 times 3 is 9 minus 6. So we have 3 vibrational frequencies. That's where the 3 rotation or vibrational temperatures comes from. So here they are down here. Okay, so Gaussian evaluates the partition function at the given temperature, which was 298.15, and in the room, the 1 atmosphere pressure, using the geometry of the rotation and vibration and electronic energy calculations. And here's the output from Gaussian. Again, this scientific notation is weird, so let's convert it all just so we can compare the different numbers. So the V equals 0, this vibrational, oh no, that's the total. So let's look at the vibrational partition function that we've been talking about today. Let me go back to the temperatures. These are the vibrational temperatures. So this is like theta 1, theta 2, and theta 3. And our partition function is T over theta, okay? So it would be, in this case, Q would equal 298 divided by 1042, okay? And this is 298 divided by 186, 866, yeah. And this is 298 divided by 5322. So our Q's are really small, okay? Now, if they ever get down to less than 1, then they're going to be 1, essentially. So they're going to be actually 1. And so we can look at our output from Gaussian, and we can see that the vibrational partition function is very close to 1. There may be slight excitation in the vibration, the bending mode. Okay. And then our translation, we did our translation in a previous lecture. We got this number. We did our rotational partition function. We got that number. And so then our total is the product of all of these. So if we take the what is this, 14 million times 2,000 times 1.033 times 1 for the electronic, okay, right here is the electronic, then we get this total. And so that's what that number is right there. Okay. So again, we're showing that total partition function is the product of all of the others. Now the electronic partition function, why is it 1? Well, again, we have to have enough temperature to excite the molecules in translation, rotation, vibration. What would it take to excite a molecule into electronic states? So let's just take the HOMO-LUMO gap. That would be the closest gap in a molecule of a filled level, the highest occupied molecular orbital to the lowest unoccupied molecular orbital. So this would be this narrowest gap in energy in a molecule's electronic energy level states. And let's take one that's really close together in terms of electronics. So one that was around 700 nanometers. So most of our substances, at least gas phase, even liquid phase, are colorless, okay, because the electronic energy levels are beyond the UV. So when we get into colored molecules, those peaks start to slide in. That HOMO-LUMO transition starts to slide into the visible range, okay? And so a 700 nanometer visible transition would be a low energy transition. That's a long wavelength transition. So let's convert that to temperature, okay? So in terms of wave numbers, 1 over 700 nanometers, let's convert that to wave numbers. And notice I color-coded this in your notes, I believe. A quick way to go from, say, nanometers to centimeters is to go ahead and put nanometers on top, centimeters on bottom, so that you know that's what you want to do. And then look at the prefix for nano, and that's 10 to the minus 9. So put it on the other side, because those are the same thing. Nano is 10 to the minus 9. Look at centi. Centi is 10 to the minus 2. This will never fail you. Okay. So if you're going, you don't have to go from like nanos up to meters and then meters to centimeters. Okay, that's 2 steps. You can do it in 1 step. If you just do this crisscross, if you have nano on top, you put 10 to the minus 9 on bottom, and centi on bottom, you put 10 to the minus 2 on top. The end result is 10 to the 7th. Okay. And so then we end up with 14,300 wave numbers. And remember, room temperature is around 200 wave numbers. We can convert that to temperature by dividing by Boltzmann's constant over Hc, and we see that this electronic energy difference is around 20,600 Kelvin. So we would need that kind of temperature to excite a molecule that had a color to it, a visible spectrum that wasn't clear. And we're not going to have a molecule that survives that. Okay. In fact, if you're doing analytical chemistry, Think about the temperatures we have in flame atomic absorption, or especially in inductively coupled plasma, the argon plasma. Do y'all remember from instrumental what kind of temperatures we had for like an argon plasma? First of all, what's the purpose of that? You've got, let's say you're testing drinking water, and you've got these compounds, they've got metals in them and so on, and you want to analyze the metals. You suck it up through a nebulizer and you run it into this inductively coupled plasma. It breaks all of the bonds of the molecules. So you have free atoms. And in fact, the inductively coupled plasma is enough to ionize those atoms. And then we're looking at the optical emission. So as the electrons go back onto the atoms, then we see the optical emission of the atoms, and we can detect, you know, all kinds of contaminants in our groundwater, like arsenic or whatever. Okay, so this tells me that the argon plasma is around 10,000 Kelvin, and this is saying 20,000 Kelvin to get thermal excitation into the lowest occupied molecular orbital in a molecule that has a really narrow gap. Okay, so it's not going to happen. What happens at 10,000 Kelvin is you break all of the molecules, and you even ionize the atoms. So 20,000 Kelvin will be even worse. I mean, it's going to really ionize everything. There's not going to be any molecules left. So we don't, that's the bottom line. You can write this down. We don't see electronic excitation for small molecules. If we have a big enough molecule, we might. Again, the larger the box, the closer the energy level spacing. So I can't say molecules, I have to say small molecules. So for small molecules, we do not have thermal excitation of electronic energy levels. So this e to the this e to the x piece of the Boltzmann distribution is going to equal 1 because it's e to the minus 0. But some molecules, small molecules, have a degeneracy that's not 1. Sometimes it's 2, sometimes it's 3. Like nitric oxide. It has a free radical on it. Okay. 1, 2, 3, 4, 5. 1, 2, 4, 5, 6. Okay. So that electron can be in that molecule with a spin up or a spin down, and essentially there's a degeneracy that's not 1. And so this molecule here, the electronic partition function for this molecule, Q of E is equal to 2. Okay, so there's your exception for, but it is this assumption that the partition function for electronic behavior in a molecule is equal to the degeneracy of the ground state. And so in nitric oxide, the degeneracy of the ground state is 2, and so that would be the electronic partition function. Now, is that important? Yeah, these partition functions are multiplied by each other. So you'll be off by 100%, right? It doubles the whole thing. So it is important to know what the ground state electronic degeneracy of your small molecule is, but most of the time it's 1. Okay, so this is the summary. We've put it all together. We've built the molecule. Yes? We really don't. No, there's a whole, and that is like a gap in the basic chemistry degree is radical chemistry. We don't do much with it. We do a little bit in polymer chemistry where we get into the free radical polymerization. Is it talked much in biochem?
No, it was really a lot in polymer.
Yeah. Yeah. And so a lot of the antioxidants that we use in our bodies and so on, the reason they work well to prevent oxidation is that they're free radical scavengers. So a lot of the oxidative processes in our bodies and in materials are initiated by free radical chemistry. And so vitamin E, vitamin C, these kinds of things that are supposedly antioxidants in our body, that's what's happening is they're scavenging those free radical reactions. Also in protecting polymers from sun damage, you put preservatives in there that are essentially acting like free radical scavengers. So that's really the extent of my knowledge of free radical chemistry. There are, I think I have, in my last job I was looking at polymer aging. And so I left there and came here after only 4 years in the job, but I was headed towards more free radical chemistry, and I have a whole book on it. But I left right at the time. I was about to get into that part, so I didn't read that book. I've got it though, but you can. So it's a whole area of chemistry that you can specialize in, and it's really important. But it hasn't pushed anything else on the chemistry curriculum out. So we still pretty much teach everything with the spin paired stuff, singlets, even numbers of electrons. We don't even really give students that nitric oxide Lewis dot structure at the freshman level because they're like, where do I put this extra electron? Everything we do is spin paired, and so it's interesting. So we have the translational motion. These are all of the pieces for the molecular partition function, which includes that volume, that nRT over P piece. We have the rotational piece, okay, with the symmetry number and the rotational temperatures, and then we have the vibrational piece with the vibrational temperatures. And you can see all of the degrees of freedom. This is the 3 translations, right? 3 translations. Here's our 3 rotations. And then here's our 3n minus 6 vibrations. So that's kind of cool. We see those degrees of freedom in this equation. So what would we have if we had a linear molecule? This piece would be T squared over theta B squared, right? Because theta B and theta C are the same, and so we would just have that one rotational constant for a linear molecule, and we would have only 2 degrees of freedom in rotation, so we would have T squared over theta B squared. Let's take some Kahoots to kind of test your knowledge. So this will be a nice check on how you're following the material. So let's go see if I can find this. Okay. Bear with me while I get the video to pick up on. Yeah, all right, that's going to work. Let's see, why is it not letting me play this one? Here we go, translation. Got it? Okay, that's good. Yeah, so the game code is 620301. Oh my gosh. That's great. Who's that? That's beautiful. That's great. Using the QR code. Don't get your finger on the camera.
Oh, you're right. I was like, what is that? Oh, this doesn't even work.
It's not working. I had to come to the middle. Yeah.
Because all the links to like, you have to pay. I don't know.
You have to pay? What?
I think it's like some other form of Kahoot. Okay, there.
Because I'm trying to do this for free. If you have to pay for mine, let me know.
Well, I think it's like a Quizlet form of Kahoot.
Oh yeah, they keep trying to get you to pay for it.
I made a Quizlet once and they tried to get me to pay for it. I said, these are my flashcards. I made them.
And they're like, this is my computer you're hosting it on.
I was just really offended.
Yeah. Yeah, it's right. I know. Yeah. Put the squeeze on you.
Really lost its target audience.
All right. It's all 7.
Soul. That's one. The dude who created Soul.
Oh, okay.
That's when it got terrible.
Quizlet? Yeah. Okay, so let's test our brains. What model are we using for the translational motion? Particle in a box. All right, very good. So let's see. All right, it's on. What justified the switch from summation to integration? Because we did that. We went from a sum to an integral right there in that graphic. I need to hear the music. Oh. All right. Very good. Very good. Okay. Yeah. All right. Where did the volume go? It was here just a minute ago. Okay.
Oh.
Oh, I thought you meant the sound. I saw numbers and I was like, oh, geez.
I like the green answer, but don't answer
It's just so.
The B went upside down. All right, yeah, so the ideal gas law, we can see that, we can show the media, and then here's the show media, right? So this V was here, and now we have nRT over P. Okay, fantastic. Okay.
Okay.
Moving up, I see the arrow, there we go. Last one, got to be fast and correct. What's the likelihood we'll see quantum effects at room temperature in translational motion? Gotta think about it. We did a calculation related to this. We did the calculation of when do we think translational quantum effects would show up? What temperature? Where Q is equal to 2. Yeah, we solved for the temperature. Oh wow! So the one person got it. It was like 10 to the minus 10 Kelvin. Yeah.
You're kidding.
Okay, so. Dun dun dun. All right. Nice. Okay. All right. The spotlight and everything. My kids always got mad at me because I always wanted to watch the video at the end of the Mario Kart, you know. They're like, come on, skip it. Yeah. So that was fun. All right, so let's do another one. See if I can.
No, we stopped here. I won.
That's right. Yeah. So let's go here. Okay. Shrink that down. refresh this. Okay. Okay, we've only got time for one. Vibration or rotation? Which one do you want to do?
Let's do rotation.
Rotation, okay, since it's sort of a lecture away. All right. Got to be quick. Got 2 minutes. I'm not getting any sound out of this thing. Come on. Y'all are stressing me out. I'm looking at the clock. So, all right, here we go. I gotta make the sound myself. All right, which of these molecules has the smallest rotational constant? You either go big or go small. You gotta figure out which is which. Now the equations are up here. Yeah, here's B, here's I. I's got the mass. Yeah, that's split. Yeah, that's split. Okay, that's good. Okay. Which of these molecules has the smallest rotational temperature? Okay. Smallest rotational temperature. So you got to ask yourself, is the rotational temperature proportional to the rotational constant or opposite, like inversely proportional? Uh-oh. So the rotational temperature is proportional to the rotational constant. Small constant, small temperature. Yeah.
That was a trick question.
Bamboozle. Okay, why does hypochlorous acid appear to be a symmetric top? So yeah, two of its rotational constants are very close to each other. So a symmetric top would have A is greater than B equals C, and B is almost equal to C. It's a thinking question. Yeah. Oh, come on. Make your choice. Make your choice. Oh, very good, folks. 5 out of 7. Or 5 out of 6. Good job. Good job. Okay, so that hydrogen is so tiny that it's mostly a diatomic. Yeah. Okay, what motion corresponds to the large rotational constant in HOCl? We talked about this. Was it the whole molecule tumbling, or was it just the hydrogen spinning around the axis? So the smaller the mass, the larger the rotational constant. And we gotta hurry.
Oh, dang,
I know, they're waiting.
Actually, I like them.
All right, come on. All right, nice. Okay, and they can come in while we're finishing up. True, false. Oh, we did this today, like a couple times. Right? Come on, answer quick. You got to be fast and correct. The faster you are, the more points. All right, good.
You know what? I'll be
And
the first to do it.
how many rotational degrees of freedom are there in a nonlinear molecule? Quick answer. Boom. Oh, big split. All right.
Fifth place. First to be last. First to be last. Last was second. Yeah, but like fifth place was last year on the board. Seventh. Yeah.
Good job. Gauss swept the day. Good job.
Hi. Shut up.
I think funny before, like,